Sorry, I think my mic was not on. Okay, so I'll start once again. So if you're not able to hear me, then please let me know. Okay. So let me start once again. So this is week 2 of Parameterized Algorithms, NPTEL course. So in this week, we have seen videos on these topics. So basically there were 5 videos: introduction to branching, analyzing recurrences, high degree branching for feedback vertex set, vertex cover above LP, and applications of vertex cover above matching. And then there is a feedback form for the learners in this course. So I encourage all of you to fill this feedback form. So this is the form. So clicking on this link, we'll be able to fill this form. So then we have this quiz assignment for this week. So there are a couple of questions. So these questions are all based on the videos that we have seen in week 2. Right. So we'll be able to attempt this quiz only if we understand uh, the material of week 2. So it is expected that you have watched this video. So is there anybody who has watched all the videos of week 2? Okay, so I don't see any positive responses. So is there anybody who has watched the first video of week 2? That is this video on introduction to branching. Okay, thank you. Shivang has watched at least the first video. Okay, so we are not going to discuss these assignments before the due date. So due date is on 9th of August. So there is instruction that we should not discuss the current assignment before the due date is over. So in today's session, what we will do is we'll look at some sample problems and we will solve these sample problems. So by solving these sample problems, you will get an idea, a flavor of the kind of problems that are expected in the exams or quizzes. Okay. So I believe you are able to see the screen. So here is the okay. This is the second question. So here is the first question that we're going to discuss. Okay, so here some statements are made. Okay, so just pick the marker. Okay, so some statements are given here. So we have to tell whether the statements are true or false. So what is the first statement? So if G comma K is a yes instance of vertex cover, okay, that means if for a graph given graph G, there exists. Okay, let me just write it down. So the first statement is saying that if for a given graph G, there exists a vertex cover. So we have already seen the definition of vertex cover. I will not repeat it here. Of size at most k, then both G minus U has a vertex cover of size at most k minus 1, and also G minus V has a vertex cover of size at most k minus 1. So that is the statement. Both these two questions must be yes instances. Okay. For UV being an edge in the given graph G. Okay. So, so you understand the question? So any thoughts on whether this is true or false? Any comments? Yes, Bala, you have any thoughts on this?
Sorry, I've just
Okay.
joined. Let me just go through. Just joined.
Okay. So you can keep yourself muted unless you are talking. Okay. So Kartika is saying it is true. The chat box. Right. So Kartika is saying that this is true. So you have this graph. On in this graph there is this edge UV, and just zoom it out slightly, and then the rest of the graph is there. So other edges and vertices are there, but U comma V is one of the edges. Okay. So this is, let us say, an undirected graph. So is it necessary that if G has a vertex cover of size at most k, then both G minus V must have vertex covers of size at most k minus 1? This is the question. So what is the meaning of G minus U? So G minus U means that you delete from G the vertex U and all the edges incident to U. Okay, this is the meaning of G minus U. Right. So observe that. To cover this edge U comma V, at least one of U or V has to be included into the vertex cover. Okay. So both of them could be included into the vertex cover, but it is not possible that neither U nor V is included into the vertex cover. Okay. So suppose U is included. Okay. And then you delete all these edges which are incident to U. All these edges you delete. So you get this instance G minus U. So if there is a vertex cover of size at most k minus 1 in G minus U, so there is a vertex cover of size at most k minus 1 in G minus U here, then with that vertex cover, let us say that S dash be that vertex cover, let us say. So let us say, just a second. So let S dash be a vertex cover in G minus U of size at most k minus 1. Okay. Then S dash union U. So you take U is going to be a vertex cover for G, isn't it? Right? Because S dash was a vertex cover for G minus U. So all the edges in G, except those edges which are incident to U, are already covered by S dash. So now if you also take U into your vertex cover or into your set, then that set will cover all the edges, including the edges that are incident to U. So definitely S dash union U is going to be a vertex cover for G, right? So similarly, if you take V into your vertex cover and you construct the graph G minus V, and you construct for G minus V a vertex cover S dash of size at most K minus 1, then S dash, S double dash, sorry, union V is going to be a vertex cover for G, right? This is going to be a vertex cover for G, right? But it is not necessary that for both G minus U and G minus V, you obtain a vertex cover of size at most K minus 1. One of them is sufficient. So suppose you take U and delete all the edges which are incident to U, and for the remaining graph, you obtain a at most K minus 1 sized vertex cover, then you are done. Even if G minus V does not have a vertex cover of size at most K minus 1, still you can output S dash with U, unioned with U, and that will act as a vertex cover of size at most K. Size at most K for G. So both what is the question asking? That both these two have to be yes instance is not true. One of them, if instead of both, the statement was one of G minus U comma K minus 1 and one of G minus V comma K minus 1 is a yes instance, then we would have said yes, this is true. But this statement is not true because it is not necessary that both these have to be an yes instance. Okay. Right. So this is not true. So do you understand, Kartika, why this is not true?
Yes, sir.
Right. So now let's go to the next question. So we'll create a page. So what is the next question? So let me just pick this question. So this is a statement. Again, we are asking the question that whether this statement is true or false. Okay, so it is probably very small. I'll try to make it large. I'll just write it down. So it is asking, is the statement is, if a vertex U of a graph G is not in the vertex cover S of G, then all neighbors of U must be in S. So this is statement. So what it is saying is, so you have the graph G. So this is the graph G. It has vertices and edges are there. Okay. So there is a vertex cover S for G. So S is a vertex cover for G. So S is vertex cover of G. So S is a set of vertices such that every edge has one endpoint in S. So if U does not belong to S, then all the neighboring vertices of U must belong to S. So because this is a set, I'll say that this is a subset of S. Okay. So is that true? Or do you understand the question first? So there is a vertex U. So if U is not in the vertex cover, then all the neighbors of U are in the vertex cover. Let us say here the neighbors of U are 1, 2, and 3. Any thoughts on this?
The statement is true. Otherwise, who is going to cover these edges?
Correct. This is correct. So what Kartika is saying is correct. So so every edge needs to be covered. So U is one of the vertices in all these edges. So all these edges that are incident to U, if U is not taken in the vertex cover, if U is not taken, then who is going to cover this edge? We have to take this vertex. Who is going to cover this edge? We have to take this vertex, no choice. So all the neighbors of U have to be taken just to ensure that these edges which are incident to U are covered. So therefore, this statement is correct. So this is true. Right. So let's go to the next question. So vertex cover on bipartite graphs can be solved in polynomial time. This is a known thing. So what are bipartite graphs? So what is the statement? So vertex cover on bipartite graphs is polynomial time solvable. So what is a bipartite graph? Bipartite graph means in a graph there are two sets of vertices, let us say v1 and v2, and all the edges are between vertices of v1 and v2. So there is no edge among the vertices of v1. So such an edge is not allowed. Or there is no edge between vertices of v2. So if you can partition the vertex set in a graph into two parts such that the edges are between vertices of different parts, then such a graph is called a bipartite graph. And this is a well-known thing that vertex cover on bipartite graphs is a polynomial time solvable problem. So I leave it to you to verify this. Okay. Right. So fourth question. So this is a statement. So given an OCT, what is OCT? So OCT is an odd cycle traversal. Okay, so this is basically a set of vertices of the graph G such that if you delete this set of vertices from the graph, and of course you delete the edges incident to these vertices, then the graph becomes bipartite. So you understand the definition of odd cycle traversal, transversal, sorry, transversal. So odd cycle transversal is nothing but a subset of vertices of the graph such that removal of these vertices from the graph is going to give rise to a bipartite graph. So this has been discussed in the videos. Uh, but we can spend some time on it, I think. Okay, so let's take an example. I mean, I'm just going to make up an example. So is this a bipartite graph? So one property of bipartite graph is that bipartite graphs don't have odd cycles. That means cycles of odd length. That means a triangle won't be there in a bipartite graph, or a pentagon won't be there in a bipartite graph. These things won't be there, right? So odd cycle transversal means a set of vertices, deletion of which leads to a bipartite graph. So as we can see in this graph, this is one graph. There is a odd cycle, a cycle of length 3. So this is not a bipartite graph. So how about this cycle? 1, 2, 3, 4, 5. This is again a 5 length cycle. How about this one? 1, 2, 3. Sorry, 1, 2, 3, 4, 5, 6. So this is a even cycle. Fine. So we're interested in removing this triangle as well as this pentagon. So which vertex should we delete? So if we delete this vertex, then this edge and this edge are deleted and along with this vertex. But this pentagon still remains. The triangle is destroyed, but the pentagon remains. So is there a vertex that we can delete that will destroy both the triangle as well as the pentagon? Maybe we'll just number these vertices. So we are interested in finding an odd cycle transversal. I will encourage you to spend a minute or so.
Since vertex cover in bipartite graph is solvable in polynomial terms, we are just removing the odd cycles by branching the L vertices, and then remaining graph is a bipartite graph, so it is solvable in polynomial time. So I think it will take 2 power L into the power constant times.
So I'm not able to get everything that you said because there is some noise at your end.
So first of all, we have to kill the odd cycles to make that graph as a bipartite graph.
Yes.
So I'm doing the branching for each edges.
Yes.
So it will take 2 power N time for branching to kill the odd cycles, because number of vertices in OCT is N.
Okay. Fine.
So the
So
remaining
that is
graph is a bipartite graph. So the vertex cover can be solvable in polynomial time.
okay. Okay. That is fine. But that is the next step of what we are going to do. My current question is, in this graph, can we delete one vertex in this graph as well as the edges incident to that vertex such that the graph becomes bipartite? Do you understand the question?
So you're asking us which vertex to be removed.
Yes, yes. Question is which
We have to
vertex?
fill the triangle.
Yes,
So we have to either pick 5, 6, or 4.
correct. Correct. So if we delete 6, the triangle will be killed. This 2 will be removed and this will be removed. But the pentagon 1, 2, 3, 4, 5, 6, this cycle of length 5 will remain. So uh, this will not be a bipartite graph. So we want to make it a bipartite graph. So if we want to make it a bipartite graph, we do not want odd cycles. So how about deleting this vertex? So once we delete this vertex, what are the edges that gets deleted? So let us say that we delete 4. Okay. So if we delete 4, then 4 gets deleted and all the edges incident to 4 gets deleted. Okay. Is that correct? And then this is containing no odd cycles. And therefore, this is a bipartite graph. So what are the two partitions of this bipartite graph? So 6, 1 and 3 are in one partition, and 5 and 2 are in the other partition, right? So deleting 4 gives us a bipartite graph. So we can say that 4 is an odd cycle transversal for this graph. Okay, right. So what was the question? So let me just look at the question. So the question is asking, given an odd cycle transversal Z of G such that there are L vertices in G, vertex cover instances G comma K can be solved in 2 to the L n to the constant time by branching on the vertices of Z. This is one option. The other thing is, so but basically these two statements are similar statements. Both are saying that by branching on the vertices of this odd cycle transversal, the vertex cover instance can be solved. But what is the running time? Here the running time they're saying is 2 to the K times n to the constant. And here they're saying it is 2 to the L times n to the constant. So we have to decide that which one is true.
2 power n into the power constant.
You mean this one? Let's call it D. Let's call it E.
D is
Right. Makes sense. Because see, the point is you are going to solve vertex cover using what? Using odd cycle transversal. And if it is going to be of any benefit to you, then the size of the odd cycle transversal will come into the running time. So 2 to the L makes sense. Because anyway, we know that the vertex cover instance, we have seen that there is a kernel of size at most K, and therefore this running time is possible, that we have seen already, right? Using that linear programming technique, right? So yeah, if you're using this technique of branching on the vertices of an odd cycle transversal, then this will be the running time, as rightly pointed out by Karthika. Okay, fine. So this question is done. So let's go to the next question. Okay, so how about, okay, so this question is about on feedback vertex set. So let me first define it formally, unless you already know it. What is a feedback vertex set? It is sort of like a cycle killer. I'll write down the formal definition. Yeah. So given a graph G, the feedback vertex set is a set X of the vertices of subset of the vertices of the graph such that G minus X is a forest. So that means you delete these vertices and there are no cycles left in this graph. So that is a feedback vertex set. You understand? All right. So here is, let me mark them. So this is statement 1, statement, that is A, B, C, D, E, and F. So let's look at statement A first. So it says that if X is a feedback vertex set of size at most K, of the graph G, then X must contain the vertex which has the highest degree in G. So let us say that the degree of a given vertex V is the maximum in G among all vertices of G. So if that is the case, the statement says that V must be included into X. So V is definitely in X. Is that true? That is the question. Do you understand the question? I believe. So let me come up with some graph and just sort of making it up, just thinking of a graph impromptu. So you want to kill cycles. So for example, let us look at this graph. So you want to kill cycles. So in this graph, let us number them. There are 6 vertices. So the degree of the 6th vertex is how much? So it is connected to every other vertex. So that is 5. So is it necessary that this vertex number 6 must be deleted in order to make this graph cycle free? You understand the question?
No, we can take one instead of 6, but 1 is not the higher degree, highest degree.
Yes. So you are saying, sorry, just a second. Yeah, I took the wrong tool. So you're saying we can kill 1. So because if we kill 1, then this edge will be deleted, this edge will be deleted, this edge will be deleted. So we'll be left with an acyclic graph, basically. But the degree of 1 is only 3. So if we kill 1, then this edge, this edge, this edge gets deleted, and we are left with this cycle free graph. But degree of 1 is only 3. So it is not necessary that you must delete the maximum degree vertex in order to obtain a feedback vertex set. So therefore, this statement is false. Is that correct? You understand? Example. All right. So what is the next statement? This is it. Assuming that G is a connected graph with the least degree 1. Okay. So that means there are no isolated vertices in this graph. X must contain the vertices which have the least degree. So it is saying that if there are no isolated vertices in a graph and the graph is connected, then the minimum degree of a vertex is 1, and it is necessary to pick all the leaf nodes, that means the nodes with degree 1, into the feedback vertex set.
The degree 1 vertex is not a part of cycle.
Correct. Therefore, it is false. Makes sense. That is true. So, for example, if we just take this, same example. So 1, 2, 3, 4, 5, 6. So this is a connected graph and there are no isolated vertices. There are degree 1 vertices. And which are these degree 1 vertices? So vertex 3 and vertex 4. But if we delete vertex 3 and 4, we essentially do not kill any cycles. So therefore, because they are not part of any cycles, for any vertex to be part of a cycle, its degree has to be at least 2, right? So therefore, there is no point in deleting these vertices or taking these vertices into the feedback vertex set. So therefore, this statement is not true. So we'll just say that this is false. Okay. So let's move to the next question, the next statement. So this is saying that X must contain all the vertices that participate in any cycle in G. It is important to note the word all, saying that X must contain all the vertices that participate in any cycle in G. Just look at this example and we'll decide whether this is true or false. So maybe
The statement is false because it is not necessary to pick all. It is enough to pick at least one.
correct. So for example, this is one cycle and the statement is saying that, okay, if you want to make this graph cycle free, then you delete all the vertices that form this cycle. But that is not necessary. For example, we have seen we deleted one and we got rid of both this and this cycles. So therefore, this statement is also false. So we move to the next question. A statement. It says that X must contain at least one vertex from every cycle in G. So the important word is at least one. So from every cycle in the graph, at least one vertex from each cycle should be deleted to make this graph cycle free. That is the statement. Is that correct?
If we are not picking any vertex from any cycle, then the cycle remains there.
Correct.
We
So if
have
there is a
to
cycle, absolutely correct. So if there is a cycle for which not even one vertex is deleted, so there is a cycle, it is formed of a number of vertices. Not even one of these vertices have been deleted, then the cycle remains. We do not get rid of the cycle. Therefore, it is necessary that we pick at least one vertex from every cycle in the graph. For example, in this case, there were this two, and let us say this is also one cycle. 3 cycles were there, and we could delete 6 or we could delete 1. So 1 is part of this triangle as well as this triangle and is part of this quadrilateral also. That is this cycle of length 4. So therefore, we could delete 1, and it is necessary that we delete at least one vertex from every cycle in G. Otherwise, the cycle will remain. The cycle will not be removed. So therefore, this statement is true. Right. So now we move to the next one. So X must contain all the vertices with degree 2. So you have to delete all the vertices in the graph of degree 2. I mean, so that is, again, we look at this example. So 5 is a degree 2 vertex.
take the square as example.
Can you repeat that, Karthika?
Take the square as example.
Yes.
Here every vertex is of degree 2, but it is necessary to pick exactly one to kill that cycle.
Every vertex is of degree 2, you are saying?
Yes, in the square.
Okay, you have drawn a square. That's what you're saying?
Yes.
Okay, that
Yes.
is true. That is true. So yeah, so she has given an example that this is a 4 cycle and all the vertices have degree 2, but it is not necessary that we kill all the vertices to get rid of the cycle. So it is sufficient to kill only one vertex. So therefore, this statement is false. Okay. So what is the next statement? Well, let's move to the next one. So g minus x cannot have more than n minus k minus 1 edges. Okay, right. So what is x?
You can use the theorem as tree has vertices of degree n having n minus 1 edges. By using that theorem, if x has k vertices, while we are removing the k vertices, the remaining graph is a torus. So it has at most n minus k minus 1 edges.
Okay. So is this statement true or false?
True.
Correct. So this statement is true. So let's formalize the argument why this is true. Uh, so if let us say for contradiction, so we are looking at the last statement. So for a contradiction, so let us say that unless you are speaking, you can keep yourself muted. Okay, thank you. So for a contradiction, if let us say that g minus x has at least n minus k edges. So that means more than n minus k minus 1 edges, right? So x is, remember, it is a feedback vertex set. So g minus x has no cycles. Okay. So because g minus x has no cycles, but if g minus x has n minus k edges, along with the fact that it doesn't have any cycles, then the number of vertices in g minus x will be at least n minus k plus 1 because it is a forest. But what is the total number of vertices in G? That is only n. And x is the number of vertices in x is at most k. So therefore, the number of vertices in G minus x is at least n minus k. Wait. I think I got myself confused. Just let me give it a thought for a moment. So for a contradiction, we are assuming that g minus x has at least n minus k edges. Fine. So at the same time, it has no cycles. So we are forced to have at least n minus k plus 1 vertices in g minus x. Because in a forest, number of
Everything is correct. The last line, the cardinality of vertices is not n minus k. it is n plus 1 because we are, yeah, that's fine. Okay. Yeah, you have done correct.
Okay, yeah,
Vertices
that's what
of
I.
G minus,
Yeah,
yes,
so
vertices of
x.
G minus X is greater than or equal to n minus K plus 1 when we are adding that X set of X vertices to that graph. It has more than, that is, number of vertices is greater than or equal to n plus 1, which is a contradiction.
Okay. Oh, I see. I see what you were saying. Oh, I see. So you are right. So let's just delete this thing. You are right. So number of vertices in G minus X is this, and the number of vertices in X is how much? But the number of vertices in X is at most K, right?
Yeah,
So if we could say something like this, I understand what your argument,
yeah.
but this is not the case. So X is of feedback vertices of size at most K. Let me just look at the question once again. Of size K. Size is exactly K. Size is exactly K in this question. So this is not less than equal to. This is equal to. That is the reason you will be able to say. So therefore, the number of vertices. So we are calling this 1, we're calling this 2. So using 1 and 2, what is the number of vertices in the entire graph? Is addition of these two quantities. That is mod x plus mod vertex set of G minus X. So that is at least K plus n minus K plus 1. So that is equal to n plus 1, which is a contradiction. So therefore, uh, our assumption is wrong. So this assumption is incorrect. And therefore, G minus X cannot have more than n minus K minus 1 vertices. So we'll just mark it true. But this is only true if the feedback vertex set size is K, at least K, I mean, equal to K is also fine, right? This looks okay to me. Yeah, maybe you can stare at it for a few seconds. Okay, so let's move to the. Okay, so this is again a true false kind of thing. So let's do this thing later. So we'll go to something more interesting. So I had plans for a couple of more questions. So almost 1 hour is done. So let me just be selective and maybe we can do this quickly. This is not a very difficult thing to do. And because this question is on matching and vertex cover, maybe this is important also. So let's do one thing. So we'll just do this thing quickly. So there are again 4 statements. So we want to answer whether these are true or false. So the first question is asking if G comma 2K is an instance of vertex cover, then if G contains a maximum matching of size K, then it also has a vertex cover of size at most 2K. Okay, so this is a yes instance. Is that true? Yes instance meaning, what does this mean? This means that G has a vertex cover of size at most 2K. So what is given to you? you know that there is a matching. You know that there is a matching of size k. So there is this is, let us say, edge one of the matching. This is some edges. So this is the kth edge. So there are k edges which are in the matching, and this is the maximum matching. That means that uh, there is no other edge that can be added to this matching. Okay. So have you seen this before?
Yes, we can pick both endpoints of these maximum edges. This is going to be cover the whole graph. Otherwise, if it is not covering the edges, there must be some independent edge.
Correct. And
Then it
then
is not a maximum matching. Given thing is not
very,
a maximum match.
very nice, very nice. So this is the correct argument. So you are right. So if you pick both endpoints of each of these edges, in this maximum matching, then you have a vertex cover. Why? Because as she said, that if it is not a vertex cover, then there is at least one edge which is not covered. So that edge, along with these k edges, will lead to a larger matching. And that is a contradiction. Therefore, if you pick all these vertices that are the endpoints of this maximum matching, then we have a vertex cover. So therefore, because the size of the matching is k, so we have a vertex cover. What is the size of this vertex cover? That is 2k. So this is a vertex cover for the graph, and therefore G has a vertex cover of size at most k, and therefore this statement is true. Okay, this was a simple thing to do. So the next question is of similar flavor. So it is asking that whether a matching of size k plus 1 implies a vertex cover of size 2k. It does not, because if the matching size is k plus 1 and you pick both endpoints, then the vertex cover size would become 2k plus 2. Therefore, we are not sure that whether there is a 2k size matching vertex cover in this graph. So these two are similar questions. So not spend much time on this. So this is false. Okay, so any graph G with n vertices has at most 2 to the k inclusion wise minimal vertex covers of size at most k. So I'm not too comfortable with the definition. Oh, so I have to.
I have a doubt on option B. Uh, you
Okay.
just take a square as a graph.
Okay.
Uh, and just name it as A, B, C, D, the vertices. I take K as parameter as 1.
Okay.
So this contains a matching of size 2. You can take AD and BC.
That is right.
And also this graph has two size vertex cover.
Okay.
So it is not a no instance, it's a S instance. It is not always correct.
No, so the question is, so I understand your argument. So the matching size is k plus 1, 2. That is right. And the vertex cover size is also 2. That is correct. But is it always true? For this example, I can understand. So for this example, is 1. So there exists a two size vertex cover. So which are the two vertices? So this one and this one, they will be considered a vertex cover, and there exists a matching of size 2. But if you so the
But
question
in the
is,
statement, they are saying always it is a no instance. Like that, the statement is like G comma 2K is a no instance. But it is not necessary by producing this counterexample.
okay, so let me give it a thought. So it is saying that if G contains a matching of size k plus 1, then G has a vertex cover of size 2k is false. So then G does not have a vertex cover of size 2k. So this implies this. So you want to say that this statement is true.
Yes, the statement is true.
So no matter what the graph is, if somebody produces a matching of size k plus 1, then there is a way to find a vertex cover of there is
No, no,
no.
I'm saying the statement is false. Like, am I correct? Yeah, the
Okay,
statement is. Yeah, I confused.
that is fine. So the state, oh, look, we'll spend some more time on this. This is interesting. So the statement is saying that if G has a matching of size k plus 1, then there cannot exist a vertex cover of size less than equal to 2k.
Yeah, the statement is false only because we are producing this example.
Yes,
Yeah, right. You are right. The statement is false.
yes.
Sorry.
No, that's fine. I also got confused. It is good to have this kind of confusions. So, right. So this example that you have pointed out itself is showing that, okay, although there is a matching of size 2, there is still uh, a vertex cover of size 2. Right, right, right. So this is acting as a counter example to the statement. So this should be false. Okay, let's move on to the next question. So it is saying that any graph G within vertices has at most 2 to the power k inclusion wise minimal vertex cover of size at most k. So first thing to ask ourselves is how many vertex covers of size at most k can exist in a graph of n vertices.
That is n choose k.
Right. So let's do one thing. Just push these things downwards so that we can just have all the question as well as the scribbles in one screen. Oh, it is. Oh, just a second. Okay. Oh no. Okay. Okay, so there are n choose k possible uh, subsets of the vertex set of G of cardinality exactly k. So the number of uh, subsets of the vertex set of uh, the graph of size at most k would be summation of n choose, maybe we can make it 0, n choose 0 to summed up to n choose k, right? Uh, so what is this sum equal to?
We can use binomial expansion, like
Correct.
1 plus 1 power k. Yeah.
Okay, so inclusion wise minimal, that I'm not really sure what it means, but of course this is not correct because 2 to the power n is much bigger. So this we can say that this is false. So if somebody makes this statement that any graph G with n vertices has at most 2 to the power k, then this thing is not there. Vertex covers, so this thing is not there. Vertex covers of size at most k, then this is answer. You understand? So even if we add this thing, it will be at most 2 to the power k. So this thing will be true anyway, isn't it? And at least 2 to the power n is too much to ask for because so many vertex covers are itself not there because of this condition that the size of the vertex cover is at most k. Does this make sense? Right, let's move to the next question. Okay. The proper k coloring of a graph G is a function f from the vertex set to the numbers 1 to k. So such that no edge has the same color on both endpoints. Okay. So a proper edge coloring is what? So you have, let us say, this is one graph. If you give the color 1 to this vertex, then to this vertex you cannot give the color 1 because these two vertices are connected with an edge. So let's give this a different color. So we can give this also same color to 2. So this one can get 1, this one can get 1, and again this one can get 2. Right, so for every edge the endpoint should get different colors, and you want to uh, use only K colors. So then that is a proper K coloring of the graph. So here it is a proper 2 coloring of this graph. Yeah, let me just double check if I made any mistake. So this is 1 2 1 2 1 2 1 2. This looks okay, right? So what is the statement? The statement says that if there is a vertex cover of size k minus 1, then g comma k is a yes instance of K coloring. That means if there is a vertex cover of size k minus 1, then it is possible to color the vertices of the graph using K colors such that for every edge, the endpoints get different colors. Okay. So is that statement true or false? Let me mark the statements as A, B, and C. So is it always the case that the K minus 1 sized vertex cover implies a proper K coloring of a graph? So let me try to give you an explicit construction. So suppose this is the graph, and some of these vertices in the graph are in the vertex cover. So this is the vertex cover. So the vertex cover size is given to be exactly k plus 1. So the size of the vertex cover is, sorry, k minus 1. So you give distinct colors to the vertices of the vertex cover. Okay. So you have used k minus 1 colors. So different colors you have given. So all these vertices which are inside the vertex cover, you have given different colors. So there are edges among these vertices possibly, but you have given different colors to all these vertices. Now the vertices which are not in the vertex cover. So all these vertices you give another color. So give a different color, different from these k minus 1 colors that are already used to color the vertices of the vertex cover. So you give a different color to all the vertices that are not part of the vertex cover. Then what will happen? So remember that the edges which are among the vertices of the vertex cover, there is no possibility of a violation of the coloring rule. That is, no edge here among the vertices of the vertex color can get the same color, because all these vertices have different colors, distinct colors. Now, how about the vertices which are outside of the vertex cover? There could be many vertices outside of the vertex cover. So remember that because this is a vertex cover, two edges which are outside of the vertex cover cannot have an edge between them, because in that case, that edge is not yet covered. But that is not possible because we have a vertex cover. This is a vertex cover. So if such an edge exists, so none of these vertices are covering such an edge. So such an edge is ruled out. So all the edges from the vertices outside of the vertex cover are from these vertices to some vertex within the vertex cover. right? And because for every such edge, the color of one endpoint is different because it's a different color from the color of the other endpoint. So there is a proper coloring of all the edges. So this is an explicit construction of K coloring for the vertices of G using this vertex cover of size at most K minus 1. So therefore, this statement implies this statement, right? Okay, so the next question is similar. So what is the next question asking? So the next question is saying that if there is a vertex cover of size K in a graph, then that essentially implies that there is a proper K coloring of the vertices. So is that true? So if it is true, then we have to provide uh, an explicit construction. Otherwise, we provide a counterexample. So I will give you a minute or so to think about it. So can you construct a graph where the vertex cover size is K, but K plus 1 colors are necessary to ensure that every edge gets distinctly colored endpoints? So let me give it a try. This is not working. So uh, oh right. Okay. Uh, Two vertices, two colors, three colors. Yeah, I mean that is right. Okay. So this is a instance. So this is a triangle. So this is a triangle. So you just let me delete this thing. So what is the minimum number of colors that will ensure proper coloring? So let's give it color 1. So its neighbors can get 2 and 2, but then 2 and 2 will be connected by an edge. So 3 colors are necessary. But what is the vertex? So 3 colors are necessary. And what is the size of the vertex cover? So if you consider this vertex, then this edge and this edge are covered, but this edge is not covered. So you have to either take 2 or 3. So the vertex cover size, the minimum vertex cover size is actually 2, but 2 colors will not be sufficient, right? So a vertex cover of size k implies k coloring is not true. Yeah, is that correct? Right. So now look at the third. Let's look at the third statement. We'll slightly speed up now. It's already 7:21. So there exists k to the mod x times n plus m algorithm for k coloring problem, where x is a vertex cover of G. So x is a vertex cover of G. So parameterized by the size of the vertex cover with the running time of k to the power mod x. So k is also another parameter. K to the power mod x into n plus m. Uh, time algorithm exists for finding a k coloring or to decide that whether for a graph on n vertices and n images, a proper k coloring exists or not. So this I think we have discussed in the video. So this turns out to be true. So you can refer to the videos for a proof of this. So yeah, so we have a couple of more questions. So maybe it will take yeah, minimum half an hour. So what I will do is slightly speed up and yeah, we'll finish with the next 1 hour. So here is a graph. So this is an instance of the feedback vertex set. So here you were asked, so k is 2. So what is it possible to remove two vertices from this graph such that it becomes cycle free? Okay. So in this lecture number 9, we have seen 4 reduction rules. So we'll apply these reduction rules on this graph. So I'll quickly write down the reduction rules. Okay, so just give me a second and to find out the reduction rules. Right. So first reduction rule is that if there is a loop at a vertex v, then delete v from the graph and decrease k by 1. So if there exists a self loop on a vertex v, then delete v and set k to k minus 1. So applying the first reduction rule on this graph, we'll delete a and we will get this graph. So we have this graph. This is P, this is E, F, C, D, and there are multiple edges, parallel edges between B and C, and K has become 1. Okay. So what is the second? So this is reduction rule 1. The second reduction rule says that if there is an edge of multiplicity larger than 2, reduce its multiplicity to 2. So what does this mean? So let me write it down. If there exists an edge of multiplicity uh, more than 2, that means more than 2 parallel edges, then reduce its multiplicity to 2. So this is basically you delete some edges, so you delete this edge. Okay, so now the multiplicity of edges between B and C is only 2. So this is application of the second reduction rule. So let me write down the third reduction rule. It says that if there is a vertex V of degree at most 1, delete V. Of degree at most 1, then you delete V because it cannot kill any cycles. So you can delete a vertex of degree at most 1. So here, which are the vertices that you will delete? So this is of degree 1, F can be deleted, and you also you do not update K, so K remains 1, right? So as soon as you delete F, so this edge also gets deleted, right? So what is the fourth reduction rule? RR4. If there is a vertex V of degree 2, then delete V and connect its two neighbors by a new edge. So if there exists a vertex of degree 2, then what you do? Vertex is called V, let us say. Then you delete V and connect its two neighbors because its degree is 2, it has only two neighbors. Connect its two neighbors by a new edge. So what happens? So which are the degree 2 vertices? D is a degree 2 vertex and E has degree 3. So D is the only degree 2 vertex. So you delete D and you add an edge here. So finally it looks like, so B and C has two parallel edges between them. E is connected to B and E and C has two parallel edges. So this is the final graph after the reduction. And you don't change K, so K remains 1, right? Okay, any doubts? Okay, so let's move to the next question. Right, so this is a simple question. So this is basically the first video of this week. The basic uh, branching technique has been depicted in this example. So you have a graph. So your objective is to decide whether uh, there is a vertex cover of size at most 3 in this graph. So you are going to branch on vertices of degree at least 3. And then after doing this branching exhaustively, we are supposed to find the leaf nodes in this search tree after applying the reduction rules. So I mean, it should be search tree. Right. So which vertex has the largest degree in this graph? So we'll branch on that vertex, which has the largest degree. Just a second. Right, fine. So there are no questions. Looking at the chat box. Okay, fine. So look at vertex A. So the degree of this vertex A is 4. Okay, so let us branch on this vertex A. What we will get is the following. We'll branch on this vertex. So we either take this vertex or we have to take all its neighbors. So this is how it should look like. Let me take blue. So if we branch on A and we take the vertex A, then we delete all the edges incident to A. So we are left with this graph, BC. Right, the rest of the vertices will be same. We have deleted A, so all the edges incident to A are also gone, but the neighbors of A are still there. So this is when we delete A. The other branch will be when you delete. This is delete A branch, and this is delete neighborhood of A branch. So once we delete A, so we update our parameter K to 3 minus 1, that is 2, right? Slightly move these things to the left to make space. So K is now 2. So the other option is to delete the neighbors of A, and with the neighbors we delete A as well. So we'll be left with Q connected to P, which is connected to R. And neighbors of A as well as A are deleted. So essentially, this triangle formed by FGH will remain. And we update K to 3 minus the number of neighbors of A. So A had 4 neighbors, B, C, D, and E. So 3 minus 4, that is minus 1. So essentially, we stop branching on this side because K is already minus 1. Okay, now in this graph, what is the vertex with maximum degree? F. So we can branch on F. So one branch will be delete F, and the other branch would be delete the neighbors of F. So delete neighborhood of F. So if we delete F, all the edges incident on F will be deleted. So we'll be left with Q connected to P, connected to which is connected to R. There is P. These edges are all deleted. So C, D, and E. And what is the updated value of K? That is 2 minus 1. That is 1. This is one branch. The other branch is you delete all the neighbors of F as well as F. So you have, this is the other branch. So Q, P, and R and neighbors of F are all deleted. So we are left with D and E, right? And we update K to whatever K was. So K was 2 here, minus how many neighbors of F are there? 4 neighbors of F. So K is now minus 2. So this branch will not move forward. Now we are left with this graph. So here we'll branch on the largest degree vertex. So we'll branch on P because P has degree 3. So there are two possibilities. We delete P, otherwise we delete the neighborhood of P. So if we delete P, then all the edges incident to P will get deleted. So we have Q, we have R, okay, and we have B, C, D, E. Okay, so P and its incident edges are deleted. This is what we have, right? And we update K. Oh, so here is a we made a mistake. So GH was here previously. So we deleted when we deleted F, we deleted its incident edges, but this edge was still there. So this edge would still be there. So this edge is still there, G and H, connected by an H. And right. And we on the other side, when we deleted all the neighbors of F, and GH will get deleted. Correct. This is okay. Right now, we have GH here also, because this was isolated from P, and K gets updated from 1 to 0 because we deleted one vertex P. And for this part, when we deleted the neighbors of P, then what is the graph will be left with? So we will have all the neighbors of P along with P deleted. So we have P, C, D, E, and G, H. And K is updated from 1 to how many neighbors of P are there? 3. That is 1 minus 3 is minus 2. So, right, sorry, P is connected to B. So B is also deleted. So P is connected to B. So B cannot exist here. So delete P. All right, so this is the final graph. So after the reduction, we have these are the leaf nodes. So now observe that K's value has become 0 or less than 0. Beyond this, there cannot be further reductions. So these are the leaf nodes. So essentially, in this graph, there are still vertices left, and that is not good. But K is still 0. But anyway, so idea of this question is to just do the branching. Okay, so this is already 7:40. So I know all of you are tired. But yeah, let's for sake of it, we'll just look at one more question. So this is what I planned. So one more question, and today we'll call it a day. Okay, so we're looking at the vertex cover problem. So this is an instance of the vertex cover problem. And we have written the linear programming relaxation. So for every vertex, if it is included in the vertex cover, that is indicated by the variable, corresponding variable. So for 1, 2, 3, 4, 5, 6 vertices, there are 6 variables. So the constraint is that for every edge, you have to pick at least one endpoint. So for the edge AB, XA plus XB should be at least 1. Similarly, for the edge BC, XB plus XC should be at least 1. So there are how many edges? 1, 2, 3, 4, 5, 6 edges. For 6 edges, there are 6 constraints. And because it is a relaxation of the integer linear program, the variables of the linear program can take fractional values between 0 and 1. So it can be verified that the following is a half integral optimal solution for the linear program given above. So if you set XA, XP, XS to half, XD to 1, and XA and XF to 0, then all these constraints will be satisfied. And also the objective function will be minimized. So what is the objective function? The objective function is the sum of the values corresponding to the variables. And because this is a relaxation, this LP optimum is a lower bound on the integer optimum. So that means that whatever is the minimum vertex cover value is at most, I'll just write it down. So let us say the optimal of OPT is LP opt, and the real vertex cover value is VC. So because it's a minimization problem, LP opt is at most. Second. Right. So correct. So the LP opt is a lower bound on the vertex cover value, right? So what is the question? The question says if we remove the vertices of V0 and V1. So V0 and V1 means, as you can see in this picture, so those vertices that have got LP value half, they are clubbed into the set phi half. Those vertices that have got LP value 1 are in V1, and those vertices that have got LP value 0, E and F, those are clubbed into V0. Okay. So if you delete all the vertices of V0 union V1, so these vertices and these vertices, if you delete DF and decrease K, that is the parameter of vertex cover problem, by mod V1. So what is mod V1? That is 1. Then what do you get? You get this instance. So you have deleted all these things. So you're left with this part, and you updated K to K minus 1. Then how much is the drop in the LPOPT value? That is the question. Okay. So what is the LPOPT value here? The sum of all these variables. So 3 variables, each with value half, and 1 variable with value 1. So the total LPOPT value would be 3 into half plus 1. So that is 5 by 2. So now after doing this transformation, you have this reduced graph. And if you write the LP constraints or the linear programming formulation for this graph and solve for the optimal, then what is the LP value you get? That we are asked. So then we will take the difference of these two. So let's write the LP relaxation for this graph. Let's call this G dash. So LP relaxation for vertex cover of G dash is the following. So what are we minimizing? We are minimizing the summation of these variables. So summation is xa plus xb plus xc. We are minimizing subject to, for every edge we have a constant. So xa plus xb, that means for this edge, uh, xa plus xb should be at least 1 because this is the vertex cover. xa plus xc should be at least 1. xb plus xc should be at least 1, right? And of course, these variables can take fractional values. So xa, xb, xc are lying between 0 and 1. So what is the optimal solution for this? So observe that if you set xa, xb equal to xc is equal to half, then all these constraints are satisfied, these three constraints, right? So half plus half is 1, half plus half 1, half plus half is 1. So what is the, and you can verify with a bit of introspection, bit of time, that this is also the optimal. You cannot get a smaller value of this optimization function. So what is the optimal value? So what is the LP opt? LP opt is summation of these three variables, that is 3 by 2 for this graph G dash. So for the original graph, the LP opt was 5 by 2. For this graph, it is 3 by 2. So what is the drop in LP opt value? 3 by 2 minus, sorry, 5 by 2 minus 3 by 2, that is 1. So this option is correct. Okay. So this is what is asking. So basically the point is, if you look at the assignment also, there are questions of this flavor that we have discussed today, right? So I hope that you will be able to attempt the quiz assignment more comfortably after this session. So after the due date is over, the due date is on, I think, right, 9th of August. So next Friday is 11th August. So we'll be able to discuss these questions as well after the submission date is over. So are there any questions at this point? Okay. So where can we get the recordings of previous and current session? So these recordings are being uploaded to YouTube. So if you go to this courses website and if you look at this thing, ask a question option, then you will be able to go to the forum. So in the forum, somebody has requested for the video recording. So here is a link to the recording. So this is the first recording. So today's recording will be shared into this channel called InfoBliss, and we will share the link as well. Okay. It would be great if you could provide more practice problems from week 1 and week 2 course material. Okay, so I will ask the team to share some more practice questions, problems for you to solve. All right. Okay. Then I think it was a long session for you. And you are Shivang. Thanks, Shivang, for being there till the end. So we'll call it a day today. See you on Friday, next Friday. Thank you for joining.